Science with Folly.
Kia ora, welcome to Science with Folly. Today we're going to continue looking at energy changes. There's three things I want you to look at this lesson. 1, moles, mass and molar mass. 2, thermochemical calculations. And 3, specific heat capacity. Are you ready? Let's go. So let's start by looking at moles, mass and molar mass. Firstly, moles. What is a mole? Not that. No, a mole is a fixed number of particles, atoms, molecules, ions, etc. A bit like if I said I've got a dozen eggs, it means I've got 12 eggs. When I say I've got 1 mole of something, it refers to a fixed number of particles. And in this case, 1 mole equals 6.02 times 10 to the 23 particles. It's a really big number. And molar mass is pretty much what it sounds like. It's the total mass of a substance for 1 mole of the substance. And you can calculate it by summing or adding the atomic masses of atoms in a substance. For example, the molar mass of water, H2O, is 2 hydrogens, which each have mass numbers 1, so you've got 2, and 1 oxygen, which has a mass number of 16. And so in total, you've got 18 grams per mole. That is the measurement of molar mass. Or, here's another one, H2SO4, sulfuric acid. You've got 2 hydrogen atoms, which equal 1 plus 1 is 2, 1 sulfur atom, which is 32.1, that's its mass, and 4 oxygens times 16 together times 4 gives you 64, the total mass 98.1 grams per mole. So here's the formula you've got to use for calculating moles. N equals M divided by M. N stands for number of moles. Little m is mass, and that's measured in grams, as you should know. And big M is molar mass in grams per mole. So if we were to calculate the number of moles in 20 grams of H2O, first of all, we find the molar mass, which in this case is 2 plus 16, gives us 18 grams per mole. Then we put it into our formula. Number of moles equals mass, which is 20 grams, divided by 18, and that gives us 1.11 moles. And we round that to 3 significant figures. Now we're going to look at thermochemical calculations. A thermochemical calculation calculates the amount of energy absorbed or released when a given amount of substance is reacted or produced in a reaction. For example, let's calculate the energy released when 100 grams of sulfur dioxide, SO2, is consumed in a chemical reaction. Here's our chemical reaction. 2 SO2 plus O2 gives us 2 SO3. The molar mass of SO2 is 64.1 grams per mole, and the enthalpy change is negative 188 kilojoules per mole. It's negative, so this tells us that this reaction is exothermic. So what do? We start off by calculating the number of moles of SO2. So we've got 100 grams divided by 64.1, and that gives us 1.56 moles. Second, we look at this equation and we see there are 2 moles of SO2, so therefore 2 moles of SO2 releases 188 kilojoules of energy, as laid out here. Next, we multiply the number of moles by the enthalpy change, and we divide it by the 2 moles that we got here, and that gives us negative 147 kilojoules. So from this, we can say that 147 kilojoules of energy is released when 100 grams of SO2 is consumed. Pretty easy. Here's the same chemical equation for the same reaction, but this time I want you to calculate the energy released when 250 grams of SO3 is produced. I've laid it out for you here. Why don't you pause the video and try this yourself? I hope you got all the answers right, because I ain't giving you the answers. Now we're going to look at specific heat capacity. And specific heat capacity is the amount of energy needed to change the temperature of 1 gram of a substance by 1 degree Celsius. The specific heat capacity of water is 4.18 joules per gram per degree Celsius. What that means is it takes 4.18 joules of energy to heat 1 gram of water by 1 degree Celsius. Different things have different specific heat capacities. What do you think's got a lower specific heat capacity, water or cooking oil? Think about it. So here's an example. When 50 grams of butane is combusted under 250 grams of water, the temperature changes from 20 degrees to 35 degrees Celsius. Butane's the gas that you use in like a gas cooker for camping. So it's kind of like maybe cooking a cup of tea or something. Calculate the enthalpy of this reaction. The molar mass of butane, which is C4H10, is 58 grams per mole. You should have been able to calculate that. And the specific heat capacity of water is 4.18 joules per gram per degree Celsius. I told you that before. So firstly, using our formula Q equals MC triangle T, we go 250 grams times 4.18 times 15, which is our temperature change between 20 and 35. If it was a negative value, we'd have to put a negative there. And our final answer is 15,675 joules. Next, we calculate the number of moles of butane, in this case, mass divided by molar mass, 50 grams divided by 58, and that gives us 0.862 moles. That means we used 0.862 moles of butane to heat the water. And finally, we use the formula triangle H equals Qn. And in this case, we've got 15,675 joules divided by 0.862 moles, and that gives us 18,200 joules per mole. So three significant figures. Normally we calculate enthalpy change in kilojoules per mole. You should be able to change that to kilojoules per mole. Right, so to recap, hope you know some stuff about moles, mass and molar mass, thermochemical calculations and specific heat capacity. Take care. Ka kite anō.
Science with Folly. Science with Folly. Science with Folly.